Hello, this is the second video in 4 videos discussing conservation of energy. This video will discuss kinetic energy and the relationship between work and change in kinetic energy. When positive work is done on an object, its speed increases. When negative work is done, its speed decreases. This means that there is a relationship between the energy of motion and work. Consider these 2 examples. When an apple falls naturally because of its weight, the weight force that's causing it to speed up as it falls is in the direction of its displacement. That is why positive work is done and it speeds up. But when you throw the apple upwards, the weight vector is still acting down, slowing it down, but it moves upwards, and its displacement vector is in the opposite direction. So the work done on it will be negative, and that's why it slows down. We define the kinetic energy of an object to be energy due to motion. It can be calculated using the formula K equals 1/2 mv squared. The units will need to be in kilograms and meters per second so that we can maintain our units of joules for kinetic energy. The total work done on an object changes its kinetic energy. So the total work is equal to the change in kinetic energy the object experiences. This is also called the work energy theorem, that says the total work done on an object is equal to its change in kinetic energy. The symbol for kinetic energy will be K, and change in kinetic energy is delta K. Example 1. A 1 kilogram baseball is thrown at a speed of 20 meters per second. If the pitcher's arm moves a distance of 1 meter, what is the change in kinetic energy of the ball? How much work is done on it? And what average force was applied to it? So change of kinetic energy is the final kinetic energy minus the initial kinetic energy. So think about this. The pitcher is throwing the ball. To start with, the ball has no kinetic energy. It's just sitting in his hand. And after he pushes and throws it, it has 20 meters per second of speed. So the final kinetic energy is 1/2 of 1 kilogram times 20 meters per second squared, minus the initial kinetic energy of 0, which gives the ball a total change or gain of 200 joules of energy. The work kinetic energy theorem says that work is equal to this change. So it gained 200 joules of work of kinetic energy because you did 200 joules of work on it. Now, we know how much work was done on it, and we can use the work formula to find the force acting on it. Work equals F times D, so force is equal to 200 joules divided by 1 meter, which is 200 newtons. But what if we're dealing with a force that changes? When the force is constant, if we make a plot of force versus position, the force is always the same. And we see that the area under the graph is equal to the force times the distance covered, or the work done by that force. So if we have a variable force, then we may have different forces acting over a different amount of distance. So the graph may be more piecewise like the one here. But still we see that if we take the area of each part of the graph under the line, then each little area is equal to the work done by that force. So work done by a variable force is just going to be equal to the area under a force position graph. And if it's a function that's not linear or piecewise, then you would take all the little itty-bitty areas until they're infinitesimally small and add them up over that curve, over the area under that curve. And then you would have what we call a integral in calculus. But in this class, we don't really have to worry about calculus, do we? We just call it the area under the curve, and you would not usually have a function like this to deal with. But one very common example is the work done stretching a spring. So remember that a spring follows Hooke's law. The force needed to stretch it is equal to the spring constant times its stretch, x. If we make a graph of force versus stretch, the force gets harder and harder, bigger and bigger with the stretch. The more you stretch it, the harder it is to pull it. So the graph would look like a linear line with a positive slope. The area under this would be equivalent to taking half k times x squared. And that is the work equation for work done on a spring. I would like to talk briefly about power. We talked about doing work in here, which is the amount of energy transferred into and out of a system. But what is power? Power is the rate that you do work at. It is the work divided by the time that it's done in. It's going to be measured in joules per second or watts. You may be familiar with a horsepower. 1 horsepower is equivalent to 746 watts.